Okay, welcome to the Friday morning session. Our first speaker is Bogdan Ganchev, and he will tell us about non-BPS superstrata or microstrata.
Okay, thank you. I first want to thank the organizers for making this possible. It's always very nice to have such meetings. They're very inspiring, at least for me. Also, I thank everybody who is attending. It's been great, and I thank the organizers who give me the opportunity to speak. Today, I'm going to tell you about some work that is based on these three papers with my collaborators, Anthony, Nick, Stefano, and Rodolfo. I think only Stefano is not here. And it's also still ongoing. So I will tell you about our efforts to go beyond BPS superstrata and construct non-BPS solutions called that we call microstrata. Okay. Sure. Okay. So this is the outline of my talk. I will first give you some very brief, quick motivation. Oh, there is also a typo. I will give you some quick motivation as to why we're interested in doing all this. We've already heard plenty of that, so I'll try to be quick. Then I will go on to review superstrata, which Nate's already did. So I will also maybe show more pictures and less formulae, but just to get everybody on track, and also for people who are maybe not experts in the field, could be useful. I will mention the main playing ground where we are doing our constructions. A special tree truncation, in which a consistent truncation, in which this a certain family of superstrata solutions fits. And then for the meat of the talk, I will focus on the non-BPS geometries that we have constructed and are trying to construct. And in particular, there are two main constructions that we have attempted. The first one, on which the papers that you saw on the previous slide are all based, and what we're currently trying to achieve, but nothing has been published on that yet. And then I will finish by discussing some possible future directions, which gets me excited. Okay, so let's start with the motivation, or whatever that is. Okay. So Hawking and others taught us many years ago that black holes have entropy. They also derived a set of rules that parallel the rules of thermodynamics, the so-called laws of black hole thermodynamics. And we know that from thermodynamics, if you have entropy, maybe you can talk about possible microscopic configurations that the system can be in. So the natural questions arises then, should we be thinking of counting some microstates of a black hole? Now, from a classical GR perspective, that might seem a bit confusing because, especially in 4-dimensional asymptotically flat, we have in certain situations uniqueness theorems that basically tell us that there's just one black hole, and that's it. Nevertheless, if you go outside of your GR bubble, as we all know, and as already a lot of people already said in this conference, Waff and Strominger did indeed count the states of some supersymmetric black holes in string theory. They did this using index techniques at vanishing G Newton. And because of supersymmetry, we believe that this index is preserved as you slowly crank up Gn. So the states that you've counted, they will remain there. Unfortunately, you don't know what happens to them to the microstructure. And one might rightfully worry, even though you're outside of your GR bubble, that still GR tells you that as you increase G Newton, matter gets compressed more and more, whereas the black hole radius increases. So maybe eventually it will all collapse behind the horizon, and you still have a black hole. Excitingly, it has been shown that if you have bound states of branes, that is not necessarily true, and the size of their bound state increases as you increase the number of constituents, the number of constituents, and the string coupling. So this suggests an interesting possibility, which is that instead of forming a horizon, maybe you will get some horizonless both stringy fuzz, which it's interesting because it's a new possibility. Certainly from the ADS-CFT perspective, we believe that every pure state on the CFT side is mapped to pure state in the Bog, and pure states have zero entropy, hence they do not have a horizon. And black holes on the other side do have entropy, they do have temperature, they do have a
Excuse me, we cannot hear anything on Zoom. Hello?
Can you guys hear us? Yeah. I'll put my computer.
Yeah, now we can.
Now I can hear.
Good. I'll put my computer and close the sound on this one, and or actually we can leave it because it doesn't work. So
it doesn't work. Okay, right.
I'll put my computer.
If it starts working, I'm sure.
I'll get the sound from my computer. Let me just put you highlighted.
But I think the slide is frozen also, no?
That is true indeed.
Yes, yes.
Magic.
Okay, that's a problem.
Oh, sorry. Wait, where is Zoom? Wait, there is no Zoom on here. I think this has been
Oh,
disconnected.
the Zoom is disconnected. Yes.
Not
here.
Okay, retry. Do we have internet? We do have some internet.
We have some internet.
Maybe.
Edurom. Live
The
stream. Got
meeting
it.
is not great.
Got it. Share. For speaking. Okay. It's all patched up by us. Yeah, they tried. They tried heavily for half an hour. Doesn't work.
Okay.
Share.
Hello. Sure. Okay. Can you see this?
We can see it now. I've got it.
Okay.
Yes,
Yes, I can now see the shared screen.
Okay, I'll keep the track.
Okay.
Okay.
Okay. Can they hear us?
You guys can hear it?
Yes, yes, I can hear you.
Okay. Good. All right, let's keep going. Anyway, this is from Nick's lectures on superstrata. This is actually a superstratum. But anyway, we want something like that. I shall just say that in this talk, I will predominantly focus on asymptotically ADS superstrata, but asymptotically flat solutions have also been constructed. Okay. Oh, wait, let me remove that thing. Come on. There we go. The way I think about superstrata, the easiest way to get to that shape that I showed you on the previous slide is you start from ADS3 cross S3, you deform it with a momentum wave that Nate's already showed you, and boom, you get this. You've already seen this in Nate's talk, so I'm gonna be very quick. I think his was 90 degrees rotated or something. But anyway, this is a superstratum, so you have three regions, the asymptotic ADS3 cross S3 region in this case, which grows linearly with R. Then you have the throat, the size of which is set by the momentum charge, which is proportional to this B squared or to the number of one of the type of strands, the plus strands in the RR picture. Sorry, no, proportional to the number of the other side that you put the momentum excitations on. And then you have the ADS3 cup that cups off smoothly and looks very much like empty ADS. And the interesting bit is here. This is where the momentum wave is. This deformation that I told you that you put on. That's where all the structure is and where the interesting stuff happens. Okay, given that you've seen this, we're not going to spend too much time on it. Same with the CFT interpretation. So, as I think Nate again said, the holographic dictionary has been worked out at the symmetric orbifold point and then extrapolated to the region where supergravity works, but where the CFT is strongly coupled. These are the states that we're considering in the RR sector or in the NS sector. The only thing I would say is that so this is the string budget, and N1 and N5 are proportional to the number of D1 and 5 respectively. In this talk, I will focus entirely on K equal to 1. The reason for this is of distributed truncation that I will be using. The reason is in distributed truncation, I will say the 1MN family of superstrata fits entirely. In distributed truncation, it's a consistent truncation on S3 down to gauge supergravity in 3 dimensions.
What's the problem with KGN1?
It's not contained in the truncation. I don't know what's the reason why it's not contained, but just not there.
If you want to get down to a three-dimensional theory, it turns out you pick one set of modes. It's because they're the simplest modes on the sphere. You could imagine doing a truncation with higher K, but it hasn't been worked out.
Oh, okay, just like that. Thank you.
Yeah. So yeah, and when I say consistent truncation, what I mean by this is that if you have a solution in 3D, you can uplift it to an exact solution in 6D and then hands in. All the sphere directions are handled by the truncation. There is a further reduction that you can kind of do. So the simplest one.
I think we lost sound again. And
Yeah.
also,
Yeah, I think it's the same. I will send a text again.
the slides don't change.
Yeah.
Okay. There we go. Guess we're back. Okay. Anyway, so yeah, and what is even more impressive is that if you restrict within one of those families to a single Fourier mode in your solution, you in fact get functions of only a single variable. So in 6D you have functions of 6 variables, in 3D you have functions of 3 variables. But if you do this, you get functions of 1 variable, the ideal variable, up to some phases that you see later, but are not important. Okay, before I continue and show you what we've done with this from this 3D truncation, I wanna ask a question. Why is this interesting? For me, at least, it was a little bit counterintuitive in the beginning, because first of all, at the end of the day, ask for more degrees of freedom. And I remember the first time I met Nick, one of the things he was telling me is that whenever you have singularities or any other type of similar problems in semi-classical gravity, that's probably because you don't have enough degrees of freedom. So he was telling me, always just put more degrees of freedom and you'll be fine. But here we're going the other direction. We are going down in dimensions and we're freezing out degrees of freedom. So that's a little bit counterintuitive. Nevertheless, it seems that the fact that it contains this family of 1MN superstrata is already an indication that something is amazing happening, and that you should look more into it. And indeed, as we will see, we have found some non-BPS geometries as well as new families of BPS geometries. And what is even more tempting is because of this simplification to having only functions of 3 variables in 3 dimensions, one can even start thinking about maybe doing some more serious numerical work in these solutions. But it certainly, at least at the moment, it seems like a lucky coincidence, the fact that all this works and all these things are contained in this 3D truncation, and you can get interesting results out of it. Okay. I will move on now onto the constructions that we've been making and attempting to do. I'll first start with the first one, on which the 3 papers at the beginning are based on. And the idea here is we take the 1,0 superstratum and we add the right moving momentum excitations to it. So the standard superstratum has left moving momentum excitations on it. And we add the right moving excitations by acting with this L-1 to the M Guido operator. So this means that your strands will carry both left and right moving momentum. When I was talking before about this 1, 2, and 3, 4 sectors, so this is all happening in the 1, 2 sector, so the top left corner, and we leave the 3, 4 corner trivial for now. So the individual constituents are BPS, but the interactions between them break supersymmetry. Okay, so that's one of the things that we'll look at. And the other thing that we will look at is stuff that we're currently working on is we'll consider 2 types of strands. So this will only have left moving momentum in this case. We're not adding right moving excitations. But they will preserve different supercharges on the right sector. So as you can see, there is a minus sign here. I just want to say that for n equals to m, this is you get a BPS state because when this is n, this thing is basically a rotation by J0 minus Guido on this state, and you just get a BPS state. But for n different than m, you get a non-BPS state. And again, interactions break supersymmetry. And the reason why we're looking, we initially started thinking about states like that is because I should also say, so the way we do this is this we put in the 1, 2 sector, and this thing we put in the 3, 4 sector. And then they interact through gauge fields. the reason we start thinking about this is because we're thinking, okay, so if we have the 1,0n superstratum in the 1,2 sector, maybe we can keep this exact and deep, and then consider this as a perturbation. But we'll get into that later. Okay, so these are two constructions that we have, and I'll start with the first one. Okay. Are we still online, Joseph?
I think so. I didn't get any message though.
Yeah,
You just changed the thing.
Okay, good. Okay, so just to give you some idea of what we're dealing with, this is our ansatz for the solution in this situation. So first we have a metric that depends on three functions: omega 1, omega 0, and k. We have also four scalars. This is scalar nu that is the seed for the original superstratum. I think it can be linked to the NS flux field. And these mu 0, 1, and 2, they are the shape modes on the S3 of the compactification. And here are these phases that I was telling you about that appear. So the original superstratum corresponds to setting omega to 0. Here we, in order to get, initially we did this in a slightly different way, but what you see is that to have regular normalizable solutions, you need to have this omega to be equal to 2m plus 1. So this is the m of that operator that we are acting with. Anyway, so yeah, so the effect is that you get this frequency in the phase. Oh yeah, and psi is just some compactification of the radial variable. So R is 0, this is 0, R is infinity, this is 1. Okay, and we also have some gauge fields that we've taken a specific gauge. I should say that so we have taken a gauge in which we've removed the Itzykson component. It turned out later that we had been a little bit too quick, in the sense that, okay, it's all consistent. This is a consistent ansatz, and it all works out. But in fact, you can have an ansatz where you have a, with the symmetries that we were imposing, we okay. Okay. And the original single mode superstratum looks like this. So as I said, you take m equals to 0 and omega equals to 1. Sorry, I said omega equal to 0, I think, on the last slide. Depends on the conventions. Omega equals to 1 is the original superstratum. And this is what it looks like. Here we have made a specific choice for the constants in the gauge fields. But anyway, that's your original Belaf 1,0n superstratum. Okay. Now, in order to go beyond this, we first will work with perturbation theory. We'll take m to be different than 0, so omega is different than 1. So we will have some interactions, and this will be a non-BPS state. You can see that at linear order, the only fields that are excited are the nu field and the mu 0 field, and they correspond to Virasoro descendants of this operator dimension 1/2 and operator dimension 1/1. And in particular, they look like this. Okay, I should say that in this tree truncation, perturbing around the ADS3 vacuum is fairly easy. you can go to fairly high orders. Well, okay. So if you fix m and you fix n, you can go to very high orders. If you just fix m and keep n general, it's much harder, but you can still make progress and go to like third or fourth order. But if you fix both n and m, then you can go to as high as you want. Okay, and there are two classes of solutions that we've discovered. Well, two classes of non-BPS solutions, and we also found another class of BPS solutions. So the first class is the so-called alpha class, where you only turn on mu at linear order. You keep mu zero turned off. And at linear order, the solution is still a BPS solution. But what happens then at second order? Interactions break supersymmetry, and moreover, it turns out that you need to turn on mu zero in order to ensure regularity of the solution. So this is something that we didn't see at the beginning in our first paper. So we didn't do this in our first paper. It was only Stefano and Rodolfo that told us about it. Not only you have to turn on mu zero to ensure regularity, but it turns out that at higher order, at fourth order, the amplitude of mu zero gets locked to the amplitude of mu in a very specific way, and we call this the special locus. We don't fully understand what the special locus is from the CFT point of view. There should be no reason why you can't have the two things with independent amplitudes, but we believe that for us that might be a restriction of a limitation of our Ansatz. So that's the alpha class, and then we also have the beta class of solutions, where you do the other thing you can do. You turn only mu zero at linear order. Again, at second order, interactions break supersymmetry. What is interesting here is that mu remains turned off, so you don't need to turn anything. This is still a non-BPS solution. However, if you do this for omega equals to 1, where you have a BPS state, you can turn both alpha and beta independently of each other, and you get a new class of BPS solutions. And we believe that in this class, if you turn off alpha, you get something that looks like NSN superstratum. And this is something that we hope to publish very soon. Maybe. Do you want the cube? Does the cube even work?
No,
No, doesn't.
just
Repeat the question. Repeat the question.
Okay.
So, of these two classes, can you relate what's going on in the green boxes to what's going on in the purple ones?
In what sense?
In the sense that, like, okay, what are you turning on in CFT language that distinguishes these two classes of solutions?
I think there's a typo in this purple box, isn't there? 011 on the right.
Oh, this should be, sorry, yes, this is a typo. This should be 011. Yes, sorry. So for alpha class, you turn on this. For beta class, you turn on this. So Emil's question was like, what do you turn on the CFT class to work in now for the beta class?
Okay.
So, and this is a typo. So the second
So I'm
stage
familiar with the terminology where one talks about plus, minus, 0, 0. Can you tell me what these correspond to?
Oh, I'm not sure. No,
This one is 0, 0. I think the other one.
This is just yeah. This is just L minus 1 to the M acting on the 1, 0 and superstratum. This I'm not sure what it is.
I mean, we have, yeah, we can, yeah, so it's an operator of dimension 1, 1. It's 411. That is made out of twist 3 objects.
And 4 fermions.
That looks like JJ bar.
Is it minus strands in Emil's language? Or?
No, twist 3, is that?
It's a linear combination of twist 3.
Yeah, it's this operator that you have omega, big omega.
Right.
Yeah.
No, but big omega is just one.
No, isn't it some? It's big sigma, I think, in David's notation.
And we fix the coefficient.
Rodolfo, isn't it the minus strands or not? The big term out.
Okay, I think it's a linear combination.
It's not just the minus.
Not just the
It's not
minus.
just
Okay. Any more questions? All right. So before I move on with some analysis, I first want to show you also going beyond perturbation theory and doing some numerics. In fact, we also solved the equations fully nonlinearly using numerical methods. And I'll just show you two plots of what we obtained so that you get some idea of what we have. So this here in particular is comparison. So we've taken omega equals, well, okay, that should be 3. Yes, slowly but surely we get it.
It's every 9 minutes.
Oh, okay, you're tracking it. Okay. Oh no.
They used to get the wrong end here every 6 minutes.
No, it's not the wrong structures. I think the
I
computer.
know, but it's still pretty disgusting.
No, after the break we'll get the computer for a real while.
Yeah.
So, okay.
Anyway, the blue curves is the microstratum, and the red curves are the corresponding superstratum where you turn off. As you can see, some of the functions are similar. Some of them develop a few more wiggles, and for different values of alpha, you get qualitatively the same picture. And if you vary omega, I think you start getting more wiggles in scalar field. Yeah. Okay. Oh, maybe you can't see. So this is new. These are the mu fields. These are all the gauge fields, and these are the metric ones.
So what is being done numerically?
Sorry, I couldn't hear
What
you.
is being done numerically?
Numerically, you solve the full system of equations. Yeah, you just solve the full nonlinear system of equations. Do you want to tell you the method?
No, they're first order equations, so you do shooting from both sides.
No, they're not first order equations. You can do.
They're second order, but they're sorry. They're ODEs, they're ODEs.
Yeah, so this is a system of ordinary differential equations, second order differential equations. Actually, I should say that so initially when we were first solving the system, because we didn't because we were not aware of this and we didn't do this, we were actually encountering lobs in our solution. And this plot here is actually something that I did last night when I went back with the knowledge that we have from Stefano and Rodolfo and obtained a solution that has no pathologies or anything. But yeah, this is just I personally started from a perturbation theory C. So you take the solution from perturbation theory and you plug it in and relax it to a solution to the full system of equations.
So second order ODEs with boundary conditions, one at infinity and one at the origin. Smoothness at the origin and
Yeah, I'll go on the boundary conditions in a little bit as well. Does that answer your question, Emil?
I think so, but it's for fixed n.
So you fix n.
Small n.
N is 2. Sorry, I haven't written this. N is 2.
As a function of the number of each kind of strand, or for fixed numbers.
No, on the gravity side, so we solve the gravity equations of motion, the bulk equations of motion. You fix n, you fix omega, you fix alpha, and you have to fix your gauge fields. And what metric you want asymptotically, because we're in ADS, so asymptotically we want just conformally flat metric. And you require that the scalar fields, the mu scalar fields, go to the supersymmetric critical point, that they vanish to infinity. For the psi fields, you require that they are regular at the origin because of the shrinking circle there. And these two, well, these two I'll go on about them. They're a bit more special than that.
Which of your parameters codes what fraction of the strand budget is momentum carrying strands?
Okay, so Amy was asking which parameter in our construction indicate is linked to the number of momentum carrying strands. Well, let me see. So alpha is the thing that determines the proportion of constituents of this type. So I guess alpha squared is proportional to n1 over n, where n1 is the number of these constituents.
And so the graphs you're showing us are for what values?
This is for well, okay, but this is, so n1 over n is on the CFT side, alpha is on the gravity side. I'll show in a bit the relation between them. This is alpha equals to 1, so it looks something like this.
We do perturbation here now.
Yeah, so these solutions were for n equal to 2. So this is some n-dependent quantity. Numerically, you only specify alpha because in the gravity you don't have the concept of n1. Then you don't need to tell gravity how many strands you have or anything. And then
Alpha equals 1 means roughly equal numbers of both times.
About 2 times more crisper than 0. About 3 times more crisper than 0.
Got it. Okay, thank you.
up to a factor of 1 over 2 plus something. Then yeah, order 1. Okay. So this is the microstratum versus the superstratum. This is exactly the same plot for the microstratum, but instead of comparing to the superstratum, I'm comparing to our perturbative solution, which is with the red wiggly dashed dot lines, whatever. So this is a solution to 9th order in perturbation theory. As you can see, it's more or less spot on it. The differences are around 1%. If you go higher in alpha, the differences become much bigger. In particular, if you're close to 2, the perturbative solution is fairly far away from the use. And it becomes very hard to do numerics as well. Okay, so this was that. Now on to this interaction that breaks supersymmetry that I've been talking about, and the boundary conditions, and what we can do on the CFT side. Okay, so as Amy was asking, you need to specify some boundary conditions for your fields to solve the Bog system of equations. But there are large gauge transformations that leave the supergravity does not care about, but they change the CFT state, which means that you need to provide some boundary data, some CFT input, in order to uniquely specify your Bog solution. In other words, you need to tell me what CFT state you want exactly, so that I can construct its exact dual, as you would expect from asymptotic ADS spacetime. And in fact, what I showed you we do this a little bit the other way around. So what we do is we solve our Bog equations by first arbitrarily fixing the gauge to something that we think is easy. In this case, we just take this frequency shift to be 0, that will correspond to the interaction energy between the different constituents.
up here running without dropping out. So
Oh, but it probably drops for a millisecond or something, right?
No, I think it drops. I think there's a ROM. I think this Windows computer has another ROM. Thing.
They don't like each other. Anyway, okay. To do this thing, you do what is called Pfefferman-Graham expansion at infinity. I have chosen different bases for our gauge fields. What's the Pfefferman-Graham expansion? You write your metric in this way. You expand it in this way. Z equals to 0 is where your conformal boundary of ADS is. And all the quantities with the 0 superscript in brackets are boundary data that you have to specify in order to have a well-defined Ishihara problem in ADS. As I already said, for the scalar fields, for the 3 scalar fields, the 3 mu's, the shape modes on the S3, we require that they go to the supersymmetric vacuum so that they vanish. For the metric, we require that it's conformally flat. For nu, we require that it goes to just alpha at infinity. And then what is left over are the gauge fields. Now, when you do this expansion, Pfefferman-Graham expansion, from it, you can read off the expectation value of the stress energy tensor. Now, I haven't shown you these expressions are basically some combinations of metric components and gauge field components. What is important is that you can link them to the H and H bar on the CFT side. You can do something similar with this and link J and J bar to the gauge field, the boundary data of the gauge field. Okay, so now because we're considering a no BPS state, there's no SUSY protection, so there's not much you can do in terms of matching with the orbifold CFT predictions. But there are still some quantities that remain preserved, and one such quantity is the momentum charge given by H minus H bar, or on the CFT side, N1 times N. And if you go back to this, you can take the difference of H and H bar, and you see that H and H bar from this holographic story will be given by this expression in the bow, where this is just some coefficient of the GT sigma component in the expansion at infinity. Anyway, when you do this, you equate the two things, you get a series in alpha, and then you invert the series, and then you get this expression that I already showed you when Amy was asking. And this is more or less a consistency check because you expect that alpha squared will go as N1 over N. Okay. Now we go to the point of the large gauge transformation and matching what the CFT wants from us for the gauge fields so that we can get the correct Bogue solution. So the large gauge transformation are roughly lead to something like that. So if you shift the phi1 field, you also shift the frequency by a similar amount, and something analogous happens for phi2. And what we do basically is we take the expected CFT values for J and J bar and 1 over 2. So we know what they are. And we use these expressions here. So as you can see here, we have only 2 of these, but we have 4 of these. But the psi 1 and 2 fields are in fact fixed at the boundary due to regularity to vanish there. So this means that in gravity, their value at infinity is already well defined, which means you have 2 parameters to fix 2 gauge fields. You do this, and you figure out what's the frequency shift. And this is the expression you get, where this C omega is given by this not terribly illuminating expression. But what is important is that this is always positive, which means that this is always negative, which means that you have you interpret the frequency shift as a attractive interaction energy between a single particle constituent and the rest of the constituents in the state. Now, this thing cannot be derived on the CFT side currently. At least we're not aware how to do this, especially given that we're considering a non-BPS state. But you can do some sanity check, namely, you look at the total energy of the state given by h plus h bar. You can derive this on the gravity side, and then you can wave your hands a little bit and argue what it should look like. So to leading order, it should be just the energy of the free particles, which is n plus 3 times n1, so there's a number of constituents. Okay, I didn't give you, but h and h bar are, I think h is n plus m plus 1/2, and h bar is n plus 1/2, and we're looking at m equals to 1, and this is the expression you get. And then the first correction that you expect is due to the interaction between the different pairs. And because we interpreted delta omega as the frequency shift due to the interaction between a single constituent with the rest of them, you divide this by the number of constituents, and then you multiply it by the number of pairs. And this thing matches exactly this. You get the same result. And this, and this holds in the regime where. So we're n1 over n is small, but still n1 is large.
Sorry, may I ask a question?
Yes, there's no.
Pfefferman Gram expansion, there is no logarithmic terms in Z in addition to G2?
No, there are no logarithms because we're in 2D. In 2D, there are no logarithmic terms, I believe. Okay. But yeah, in even dimensions, usually you have log terms. Okay, even dimension is 57. Yeah.
Even dimensional in the boundary.
Yes, but when it's 2D, I think you don't get any. Okay, any other question? Okay. I have 15 minutes, Yossi?
No, I think so. No. You started at 10:15. So.
Okay, okay. And how many minutes until this?
No, it will crash through.
Okay, good, quickly. Okay. Oh, sorry. Yeah. Well, this was everything I want to say about the first type of construction that we've done. There are other interesting points that one might discuss about it, like the special opposites origin, what it means. But I'm not going to go more into that with respect to time. And also, Anthony will be telling us more about yeah. Sorry, this touch part is really not collaborative. Okay, we're back. Nice. Anyway, so what do we have here? This project is not finished yet, so I'm just going to give you some flavor of what we're doing and what we hope to get. But as I said, this is in the 1-2 sector of the theory, top left corner. This is in the 3-4 subsector, bottom right corner. The situation is very similar to our previous situation, even though we don't have these L-1 twiddles. This just basically means we don't have right moving excitations, which is why the omegas in both sectors. So when you see 1-2, one refers to quantities in the 1-2 sector, and two quantities in the 3-4 sector. So omega is by default just 1. Anyway, in both sectors, you can have both alpha and beta class solutions again, which means you have slightly more possible combinations of things you can do. Furthermore, something that we decided we're going to do to simplify our lives is we realize that we can go to a gauge where we observe all these mode numbers n and m, and well, okay, these are just constants, but you can observe all these things in your gauge fields. You just shift the constant terms in the gauge fields, which means that your equations do not have n and m in them. And in fact, n and m enter as boundary conditions on your gauge fields. And in particular, it will be the psi gauge fields, at the origin that will be giving you an NM. Okay, so first I want to show you for the alpha alpha and the beta beta class, which means that you have alpha in both sectors, 1, 2, and 3, 4. Again, as before, we have nu1 and nu2 turned on only at linear order. As before, so lambda 1 and 2 are the equivalent of mu0, just for the two different sectors. Again, has to be turned on to assure regularity. And again, their amplitudes are locked to the amplitudes of the nu1 and nu2, so you again have this special locus thing. One interesting thing, though, however, is that when you do the perturbation theory, I think we went to 6th order, and you stare a little bit at some of the results, you realize that for some of the scalars, you can resum the perturbation theory series, and you can obtain exact expressions. And then you can go back and plug this in your equations of motion and see what you get. And by going through some painful amount of algebra, you actually manage to simplify the equations to a situation where all the gauge fields from 2nd order ordinary differential equations become 1st order ordinary differential equations. On top of that, the K function in the metric also satisfies the 1st order differential equation, and a linear combination of omega 1 and omega 0, the metric components, also satisfy 1st order linear equation. And one thing you can observe is that because we absorb these things in the gauge fields and they don't appear in the equations of motions, in fact, also I said that when you take n equals m, you get a BPS solution, BPS state. This means that the equations of motion are exactly the same whether you're looking at the BPS or the non-BPS state. And the only thing that determines whether you're considering a BPS or a non-BPS state are your boundary conditions. And so we for some time tried thinking that maybe you can reduce all the equations out to 1st order differential equations. We couldn't do that. But nevertheless, this seems similar to something that I think Nick and Josif tried some time ago, called almost BPS solutions, where you take a BPS solution and you change the base metric, and you just take all the functions to satisfy the BPS equations apart from the metric functions where you just change something, and you get non-BPS solution. So this seems similar to that. And also these drastic simplifications means that one can hope to do some numerical stuff if possible. Anyway, moving on from there, the beta beta class, very similar situation as before. You activate the equivalent of mu0 in both sectors at linear order. The nus remain turned off, as well as some other fields. In fact, there are a lot of fields that get turned off, but we haven't had the chance to plug all that back in and see whether you can simplify again the equation similar to here. But what is interesting is that, so I didn't mention it, but for the previous construction, in the beta class, in fact, we managed to obtain an exact analytic solution. Nick managed to solve the equations. So what we thought here is that, well, in the 1-2 sector, you can put this exact beta class solution, and then you can look at a linear perturbation in the 3-4 sector with this thing. And what happens is that only the lambda 2 field is excited at linear order, everything else is not. And you can do some double KB analysis to try to figure out the dependence of the interaction energy for large frequencies. I am not going to say anything more about that. Maybe Anthony will say something on Monday. Anyway, I'm almost done. The only thing I wanted to show you is something that I also managed to do last night. So, okay, first, before I go into this, a caveat. So, in this situation, in this case, we still haven't quite figured out the large gauge transformations and the unique determination of the Bog solution in terms of CFT data, because there are just more components and we're missing something. So the approach that we had before, where we choose some arbitrary gauge, find a solution, and then shift back to whatever to the correct CFT values is not something that we can currently do. So this plot that I'm showing is modulo this COVID, because this is again a full numerical solution of the system for n1 equals to 2 and 2 equals to 3. Sorry, n and m. These are n and m, and then alpha 1 on the alpha 1 equals to 1, and alpha 2 equals to 1/10. So the idea is that you have a deep superstratum on the left, and you perturb by something small. And you solve the equations fully non-linearly, and you get these blue curves. And the red dashed dotted curves that you see are the perturbation theory result. This here is only to third order because it's a little bit harder. It's also for general N1 and N2, N and M, sorry. But as you can see, for most of the fields, it matches pretty well, but for some of them, it's quite far off. In particular, for this one and this one, I think what happens is that up to third order, they are basically just some constants because in perturbation theories, you haven't seen the functional dependence, and that. Oh, okay. I thought it was 9. That's why I had calculated it. Anyway, this is my last slide. I just wanted to say, to give some conclusions and say what possible future directions. So what we're doing is still very special in the sense that we are in a 3D setting, considering a single family of superstratum solutions and considering a few simple states. But we can still get some non-BPS states, which is exciting. And some new BPS solutions, also BPS superstrata that we've managed to derive analytically, and possible future directions from all of this. So for me, the exciting thing is that I think this just shows that there is something in this truncation, and one should definitely try and explore how much you can get out of it, and then figure out how to expand on it or move on from it. And one way of doing this, for example, is this type of ansatz that we did. I mean, this might be something that one can consistently do even in 6D, where you won't have all these. I mean, of course, it will be more complicated, but you won't have the limitations of the 3D ansatz. And so I was only talking about single modes superstrata, and introducing only a single frequency. But you can imagine that you add 2 Fourier modes in your superstrata family, and you do the same thing. Of course, then things won't be functions of one variable only. You also have time dependence. But maybe you can do some perturbation theory. Maybe you can do some numerical stuff. Paulo Pani seemed interested in this, for example. And maybe you see some, I don't know, get behavior, I don't know, mixing of energy levels, I have no clue, repulsion, I have no clue. But that's definitely exciting. Analytic solutions, as I said, we managed to derive a generalized, we haven't published that paper yet, but hopefully it will be out next week, of some new class of generalized superstrata states that depend on both the mu and the mu0 on alpha and beta. And the equations, the way you get to the equation is very similar to what we get in this almost BPS case for the alpha-alpha class here. So I personally am still a believer that maybe you can get an analytic non-BPS solution, but who knows. Anyway, of course, you can try to do some type of force calculations in these backgrounds. You can maybe try to see whether you can actually do some safety calculations for these non-BPS states. I know that's incredibly hard. And the other thing you can do is you can move on from these simple states and maybe consider directly a non-BPS perturbation of a deep superstratum and see whether you get some qualitatively different. Anyway, that was my talk. I forgot to put a thank you slide, so thank you.
Questions?
I might just add one comment. I mean, one of the things that's really interesting about this is you see that as you turn on these BPS breaking parameter, the frequencies all shift down, and the frequency shift downwards depends on the amplitude of the mode that you've turned on. And so, in a sense, this is where you might begin to see some transition to chaos, because what you have is the spectrum of the states is now depending on the amplitudes of those states, and in fact quadratically, in this order. And so if you imagine turning on a whole bunch of states, everybody's going to shift differently in response to everybody else. So rather than having this rigid spectrum that you find in supersymmetric things with high degeneracies, turning on the non-BPS shifts the frequencies all over the map depending on the amplitude of everybody else. So,
yeah, this is linked to, I think, this point, right?
Yeah, I think this is the really cool thing. I think you get parallel interest in this. That you turn on a couple of these things. It's also related to this thing we call the special locus. The special locus is precisely being tuned so that we don't, so that the two modes we turn on remain in lockstep with each other. But once you move away from that special locus, we expect really chaotic beginnings of the spectrum.
But don't you get non-normalizable modes? I mean, isn't the special locus the place where the...
Yeah, you get non-normalizable mode. Okay, so this is the reason why the system is screaming at it. So to make this equation solvable, these two modes have to be double. One has to be twice the frequency of the other.
But that's a limitation of the Ansatz.
That's the Ansatz, because we want to reduce it to single ODEs. PDEs are nasty. So to reduce it to ODEs, we have to have these two modes with one with twice the frequency of the other. But we expect that in reality, in a generic perturbation, that 2-to-1 ratio will not be preserved.
I mean, on the CFT side, like, you don't expect that the quantum corrections to these energies will be proportional to each other.
Ansatz, if you break this, and
we can't do the calculation. So the point is, we'd like to do
what happens is you get time dependent, so you're not anymore just function of one variable, and things become much harder.
So the appearance of non-normalized modes is the usual sort of thing. You force something into a pot that it doesn't want to be in. It doesn't want to preserve a 2-to-1 ratio. So it screams at you by producing log terms of infinity. And really what almost certainly is going to happen is that they will just develop frequency shifts that are independent of each other. And that's what we'd really love to see. But the general statement is that once you go non-BPS, everybody's frequency seems to shift. They all seem to shift downwards because of the blinding energy. But they shift downwards by different amounts depending on who they are.
so that's what it.
Yeah, so that's the beginning of chaotic spectra, I think.
So, so, have you looked at different values of little n?
Little
n, the number of L-1
Yes, I mean, you mean perturbatively for sure. So all these results that you see here, these are for general n. So we have derivation theory up to 3rd order, for all the functions up to 4th order it becomes very hard. But we also have similar plots. Well, not exactly similar, but we can easily do this for different values. And this is n equals to 2, but you can do higher.
Can you make some qualitative statement as you start piling little n be bigger, sort of piling more mass without adding momentum?
I don't think we have reached any high n in well, okay. Yeah, go on.
You can take some of the geometry sort of getting more, compacted and deeper because you're sort of adding more energy, but not supporting it with angular momentum.
I don't think we've actually checked that. So certainly we can. I don't think we can do the numerics to a high enough value of n where you see anything interesting. But as I said, we have perturbation theory results to high order, and there I'm sure we can check that. Why are you interested in that?
Just to start seeing, that's a sort of a direction start moving to start seeing the gravitational collapse.
Mm-hmm.
You would expect that if you start out doing something else, that eventually the bottom will fall out, you get some closed trap surface, and it'll want to run away to a black hole. Within the
No.
supergravity approximation.
It will not. Okay. I don't think it will.
I mean, you can increase energy also by keeping n fixed and increasing the value of alpha, right?
Right.
I mean, that's a big-
But eventually you run into CT6, so you have a CT6.
But before you run the CCCs, the thread gets arbitrarily deep. You can get to arbitrarily high redshift with geometries from top to bottom. So these geometries typically have this long ADS2 times S1 thread with a cap at the bottom. So they look very similar to superstrata. They just have all this other qualities.
So, okay, so maybe I could ask the question that way. If you go to n equals 2 versus n equals 1, does the throat get a lot deeper?
I think it's the trade-off without you've got this parameter alpha, which you can dial up, which is the amount of the nodes you've got, and you put n equals 2. I think you can dial up alpha
If
quite slightly.
you keep alpha fixed, you wanna, I mean, if you increase n, I presume it's going to get deeper. But I think it will be less pronounced than if you're playing it out.
Yeah, it crashed again, by the way.
We should probably.
It probably stops.
Any other questions?
Yeah, this come back to 12. So